Let's talk about gravitational potential energy. We've already mentioned gravitational potential energy and kinetic energy in the last example in the last lecture. So let's get into a little bit more detail about what this actually means. We'll start with a quick review of gravitational potential energy from an algebra-based physics course. This is a quick review for some of you, but for others of you, I'll go into a little bit more detail about what gravitational potential energy is. Let's say we have a book of mass m. We lift it vertically upwards with a displacement h by some external force, let's say you or me. And we lift it up at a constant velocity. How much work does that external force do on the book? We've already covered this before. We take F dotted with the displacement. So we apply Newton's second law to the free body diagram. The sum of the forces equals the applied force minus mg, which is equal to 0 since we're moving at a constant velocity. That means that the applied force is equal to mg, mass times the acceleration due to gravity. Again, the definition of work is F dot d. This means we multiply this applied force, mg, with the displacement that's in the same direction. Since we're applying a force upward, and the displacement is upward, our work should be positive, and it'll be mg delta x. But again, we're moving a distance of h, so we replace the delta x with h. So the work done in lifting a book at a constant velocity is mgh. If we apply the work-energy theorem to this, the initial energy plus the work done is equal to the final energy. If the book started and finished at rest, that means that we have no kinetic motion, no kinetic energy. And that means that the initial energy had to be 0. Then our equation becomes the work is equal to the final energy. But we just showed that the external force did work. It was mgh, lifting the book. So that means that the final energy is equal to mgh. We conclude that the energy of the mass is increased by an amount mgh when it's raised by a displacement h. The name for this form of energy is called gravitational potential energy. We use GPE to represent gravitational potential energy. One important thing to note is that changes in gravitational potential energy are important, but their absolute value is not. This is because h represents delta h, or a change in the height. You may define any point to be 0 meters in height when it represents the original position of an object. This would give you 0 gravitational potential energy at that point. But no matter what height you choose to call 0, changes in height will still result in changes of gravitational potential energy. Remember, choosing your reference point is really important when we're talking about energy. If we chose the ceiling as the reference point, then all of the energy that we had in this change in gravitational potential energy would actually be negative because it's below the reference point. So choosing a reference point is kind of important when solving these problems. One more thing. The gravitational energy of the system, or potential energy of the system, is conventionally defined as the negative of the work done by the field of the system, whether it be gravitational or electric. How is this related to the derivation just performed to show that gravitational potential energy is equal to mgh? Our calculation used the work done by external force. The conventional definition uses the work done by the force exerted by the gravitational field. The gravitational field force is the force due to gravity. And that's negative because the force is going down. By taking the negative of this work, you get the same result, which is a positive gravitational potential energy. The book is moving up at a constant velocity and travels a displacement h. Note that the force exerted by gravity is in the opposite direction of its motion. It's anti-parallel. So the work done by the force of gravity is actually going to be negative mgh. The gravitational potential energy is negative the work done by gravity. So therefore you see we have mgh, which of course gives us the same result as the previous example. So let's go through this again just to make sure. If we look at the work done by the gravitational force, that's going to be mg in the negative j hat direction, dotted with the displacement, which is in the y j hat direction. If we take negative j hat and dot it with j hat, we get negative 1. So when we find the work due to the force of gravity, we end up with negative mgh. Gravitational potential energy is defined as the negative work done. If the work is negative mgh, and we take the negative of that answer, the gravitational potential energy would be mgh, a positive value. What is the change of gravitational potential energy for a 5.0 kilogram object which is raised from an initial height of 1.0 meters above the floor to a final height of 8.0 meters above the floor? Let's take a look and see. We know that the change in gravitational potential energy is equal to mg delta x, or in this case delta h. We have mg times h final minus h initial. We substitute in the numbers, and we end up with a gravitational potential energy of 340 joules. What is the change of gravitational potential energy for an 8.0 kilogram object which is lowered from an initial height of 2.1 meters above the floor to a final height of 1.5 meters above the floor? The gravitational potential energy is equal to mgh. The change in gravitational potential energy is equal to mgh final minus mgh initial. Substituting in the numbers, we end up here with negative 47 joules. Notice that we do end up with a negative number here, and we should. Our final height is lower than our initial height, and this means that the change in energy will be negative. We're losing energy as we lower the book, or the object. What is the change in height of a 2.0 kilogram object which gains 16 joules of gravitational potential energy? Pause the video now and see if you can answer this on your own. Okay, let's see if you were correct. The change in gravitational potential energy is mg times the change in height. We solve for delta H, which is the change in gravitational potential energy, divided by mg. Substituting in our numbers, we get a height change of 0.82 meters. Notice that I did not put in a negative 9.8 meters per second squared. Energy doesn't have direction. We're using the magnitude of the acceleration due to gravity for these calculations. A librarian takes a book off a high shelf and refiles it on a low shelf. Which of the following explain the work done on the book by the librarian and the Earth's gravitational field as its GPE, or gravitational potential energy, is lowered? Select two of the answers. Pause the video now. Okay, let's see if you chose the correct answers. You should have chosen B and C. You are doing negative work because you're lowering the book, and the gravitational field does positive work on the book. B and C. Let's put together the concepts of two-dimensional motion and forces with gravitational potential energy. We're going to use a box being pushed up an incline as an example. It all depends on what we can measure. Assume it's easier to measure the displacement of the box that you travel. How do we find its change in gravitational potential energy? As you can see from the diagram, we're probably going to have to use trigonometry. The box starts with no velocity, and after it is pushed up a displacement d, the box slides up and is momentarily stopped before sliding back down. Does the gravitational potential energy equal mgd? No. Remember, the formula for the gravitational potential energy was calculated from the work formula, and it assumed the gravitational force, or the force that opposed it to lift the object, was in the same direction as the object's motion. The gravitational force points down. Since work only includes the distance and force components that are parallel, delta GPE involves h, not d. So how do we calculate h when we have d? Well, we can see from the triangle here that if I take opposite over hypotenuse, which is the sine of the angle theta, that will give me h divided by d. So h is going to be equal to d sine theta. A 5.0 kilogram block is at the top of a 6.0 meter long frictionless ramp, which is at an angle of 37 degrees. What is the height of the ramp? Pause the video now to solve this problem. Okay, let's take a look and see if you have the right answer. The height is equal to d sine theta, so we take the 6.0 meters and multiply by the sine of 37, and you should end up with 3.6 meters. If you've done this correctly and you do not get 3.6 meters, check and make sure that your calculator is in degree mode and not radian mode. The 5.0 kilogram block slides to the bottom of the 6.0 meter long frictionless ramp, which is at an angle of 37 degrees. What is the change in its gravitational potential energy? Go ahead and pause the video now and see if you can come up with the answer. Okay, let's see if you were correct. The gravitational potential energy is equal to mg times the change in height. We also know that here we have, we're going to replace the delta H with d sine theta, okay? And we end up with negative 5 kilograms times 9.8 meters per second squared times 6 meters times the sine of 37 degrees. This gives us negative 180 joules. Can you figure out why this should be negative? That's right. The final height ends up 0, but we do have an initial height. When you take 0 minus a number, you're going to end up with a negative number. In the next video, we'll cover kinetic energy and elastic potential energy.